Hi everyone. Today I'll talk to you about some pitfalls, subtleties, and techniques when doing automata-based constraint generation. This paper is more like a collection of rough edges and tricks that we encountered when trying to use constraint generation for our own research. Taken together, they led us to implement our own small framework so that we could be sure things worked the way we expected. We hope that they can help you as well when using or implementing constraint generation. A problem with LLMs is that they assign non-zero probability to all sequences. So if you ask it to generate an output in some specific format, it often will, but it isn't guaranteed to, no matter how you prompt it. Constraint generation is a technique where language models can be forced to output text that matches some syntactic constraint like JSON or code or multiple choice answers. It basically works by having some schema oracle that we can use to check if a token we are about to sample would cause us to form an output that can't possibly satisfy the constraint. In constraint generation, when sampling, we assign zero probability to all tokens that don't satisfy our constraint and assign the usual probability, maybe with some scaling involved, to valid tokens. This ensures that syntactically invalid sequences have probability 0. Constraint generation is obviously a powerful tool since it gives you verifiable structured outputs, but it has a lot of rough edges. Basically, tokenizers are hard to implement and parsers are hard to implement, and so the intersection of tokenizers and parsers is definitely going to be really hard to implement. However, we found that automata actually capture a lot of the functionality needed to implement constraint generation. Since automata are really well understood and they have many high-quality implementations, we found this to be a good framework to start with. There are a number of really great constraint generation packages already out there. For example, Outlines is a fully featured library that uses automata as its base. On the other hand, Guidance is another full-featured library, but it uses a dynamic grammar as the constraining backbone. And Xgrammar is another that uses a hybrid approach. Many of the rough edges in our paper were observed in these libraries, which goes to show how difficult it can be to get it right. One thing we want to note is that our work is not meant to compete with any of these frameworks. These frameworks all do constraint generation and build many other things on top of that, while we only focus on the very core of constraint generation. Here's an overview of the main techniques and pitfalls that we discuss in our paper and why they're important. One thing to note is that many of them are specific to the actual tokenizer that you're using, which makes things very complicated from a user and maintainer perspective. We found that using an automaton framework allowed us to modularize a lot of the problems here to reduce the burden on the user and the maintainers. I'll briefly introduce a few of these issues in this talk. At the core of our approach is a finite state transducer pipeline, where we compose many different modular automata in a row to implement all the features that we want. On the left is the actual pattern that a user wants to restrict the LLM to. Then we have some pre-processing, for example, filtering out some bad text or aligning the text with the tokenizer expectations, before we do subword promotion. This step is useful in that the user describes the pattern at the character level, but LLMs actually work at a subword level, so we need some way to match the granularity without requiring the user to write a complicated subword level regex. A simple character-to-subword transducer is enough to promote patterns to the subword level. Finally, we have a canonicalization automaton that filters out bad subword sequences or allows us to restrict to not only sequences that match the pattern, but also what would be the canonical tokenization from the tokenizer. Each of these components is modular and can be extended at will just by using regular techniques from automata theory. Here's a quick example of the pattern and subword promotion steps without any pre-processing. A user describes a pattern that's a regex, which we convert to an automaton. Then we use a transducer that maps character sequences to subword sequences and compose them to get a subword level automaton. If you take any accepting path in the subword automaton and detokenize it, it would form a character string that matches the original character level automaton. Canonicality filtering extends this by only allowing paths that would match the tokenization. For example, here is a subword automaton that encodes all the possible ways to tokenize Amazon and Alphabet, but only the dark paths correspond to the canonical tokenization of these words using a BPE tokenizer. Recently, a way to form a BPE automaton that only accepts canonical subword sequences was found, and so it can be composed with the subword promoted pattern to only accept valid and canonical sequences, even if the pattern describes an infinite language. One often overlooked aspect in constraint generation is that tokenizers tend to have a pre-processing step that slightly modifies the input. The user might not be aware of this, so it would be better if this could be included as a tokenizer-dependent modular constraint by the maintainer. Here's a simple example for Llama 2, which prepends a dummy space symbol and replaces all spaces with a thick underscore. Note that some tokenizers have far more complicated processing steps, and some are even non-regular, so this technique can't always be used. Constraint generation tends to allow any valid subword sequence that matches the constraint. Additionally, you can prompt the model with information about the constraint, but it is difficult to properly condition it. So what happens is that the model tends to generate things as normal, but then suddenly runs into a wall imposed by the constraint and has to scramble to get out of it. Here's one example that we encountered very frequently. The Llama 2 tokenizer encodes digits one by one, usually with a space in front of it. So imagine that we had the prompt in Roman numerals, XVII means, and we constrain the model to output anything but numbers. The model doesn't know this a priori, so it starts generating as usual. The highest probability next token by far is the isolated space, in preparation for generating a digit. If we sample that, there are no valid digit subwords, so the model suddenly has to try generating something else. It will eventually correctly spell 17, but using a very weird and very low probability non-canonical tokenization. What if we had just banned isolated spaces as well? Then the model is much more likely to output the canonical sequence for 17, which has super high probability. A related technique brings us back to canonicality. First of all, if we had enforced canonicality in the previous example, then the isolated space issue would have been basically resolved. But there's another benefit to canonicality. Notice that for all but the start state, the states that the canonical paths reach have only one valid outgoing arc. This means that we don't actually even have to sample at all. Since only one token is valid, we can just deterministically select it and skip to the next state. Outlines was the first to discuss this technique, which they called coalescence. They described some heuristic algorithms to compress paths in the automaton in order to find spots where deterministic generation could be used. Canonicalization subsumes all of these heuristics and verifiably finds all instances where we can skip generation. Here's an example we tried with the JSON schema, which are good examples for this because they contain some sections that are hard-coded and thus amenable to coalescence, and some sections which are free-form. We used two different sized llama models and sampled JSON from the schema while recording how often we were able to skip generation when using canonicalization and not using it, and also the relative speedup. We can see that canonicalization allowed for more than 3 times as many deterministic generation steps, which led to a more than 15% speedup in inference time. We implemented our own very lightweight constraint generation package after running into many of these issues. Here are some examples that show it is able to take in a model, extract tokenizer information, apply a user-defined pattern and some other modular constraints like the ASCII constraint. Then, we can give it a prompt and sample responses. We also implement constraint marginalization, which, to the best of our knowledge, is not present in any existing constraint generation framework. Constraint marginalization allows us to correct for the warping in the autoregressive distribution caused by the constraint logic manipulation. Our framework allows for exact marginalization by enumerating the valid subword sequences under the constraints, as well as approximate marginalization via importance sampling. This library is also made available with our paper. Here are the main issues and techniques covered in our paper again. Overall, there are many subtleties to constraint generation that you should be careful for, so we hope that this has been helpful for you. Thank you.